this semester. They won't always be announced, so that gives you some added incentive to come to class. You just turned in homework 4, and I was telling somebody yesterday that that problem, well, the second problem, that assignment, is probably like the biggest brain teaser of the semester. You know, we will have more complicated material. Like at its essence, that second problem from the homework yesterday, it's not complicated. It's just like the logic. You have to kind of figure out a couple of if-then statements to know like the head and how the flow direction you've assumed affects whether head is being lost or gained. And so I do recognize it's tricky. You know, my solution of it I think is 4 or 5 pages long. You know, in a sense, an instructor for a course is kind of like a personal trainer sometimes, and there's just a level of complexity that students have to become comfortable with before they graduate and enter the engineering profession. Just like a certain level of like calculation detail has to be normalized for you. And so, you know, we don't give you big homework assignments because we're sadistic. We are sadistic, but we don't give them to you because we're sadistic. We give them to you because we want you to become strong. We know that you're capable of doing good things. You're going to make it through the program at this point. Anybody who makes it into the junior year of engineering is going to graduate. So you're going to make it. We just want to make sure that by the time you graduate, you've got the skills and the resilience that your employers are going to expect out of you. So that's kind of the wrap up for that homework number 4. Homework 5, I think you'll find a little bit less calculational intense because you're going to be solving that one mostly with Excel. That's just a Hardy cross problem. I haven't posted it on Blackboard yet. I'll do it right after class, but that's going to be due on Friday of next week. So you've got a little bit of added time there because of the it being February break on Friday. So we're going to be done talking about the things that go into the Hardy cross method after today's class meeting, but then you'll still have more than a week to finish the assignment. Any announcement-related questions before we pick back up on this example from last time? I suggested that you save your file. This is kind of to refresh your memory. This is the problem that we were working on, where we had this pipe network, and we're trying to find out what are the flow rates through the network, and we were given the pressure at one of the junctions. We were told what is the pressure at junction A. So I kind of hurried through the last steps needed to find the flow rate through each pipe. Let's just revisit what that looked like. So remember that it all kind of started with me putting in these guess values of the flow rates. And so clockwise is positive, and you know, we set up the pipe material constants that don't change, like the relative roughness, diameter, cross-sectional area, length. In our first iteration, we were estimating the F values using the fully turbulent flow assumption, which just assumes you've got a high Reynolds number, and so therefore the F value is dependent on the relative roughness. Then in the second iteration, we started using the Full-Jane equation for F value calculations. And then the other kind of tricky thing that we kept track of, who can remind us why certain pipes were in bold? What was the reminder I was intending by putting this in bold? Yeah. They're in both loops. And so CE is in both loop 1 and loop 2, and EF is in loop 1 and loop 2. And so why is that significant? What do I have to remember to do when it comes to the flow rates with those two pipes?
They're switching direction.
Switching direction. Now look at the estimate for the flow rate. Here in loop 2 of iteration 1, CE and EF, I didn't use my initial guess of the flow rate. I used the most up-to-date estimate of the flow rate. And so you need to keep that in mind, that you always use your most recent estimate of the flow rate. And so for pipe CE, I got that most recent estimate of the flow rate through the loop that we had just finished from loop 1. And so I said that the flow rate is the negative of pipe CE in loop 1. Same thing with pipe EF, the negative of that other estimate of EF. Okay, so then in loop 1, iteration 2, I apply that same thing where I'm just getting the most recent guess of the flow rate, and when it comes to the common pipes, I referenced iteration 1, loop 2. So once I kind of set things up in loop 2, then I could just copy and paste the whole thing to do loop 3, to do loop 4, and then what we saw is that the change in flow rate for these pipes was getting negligibly small. There was not any additional change from the input and the output because the correction factors were getting so small. Okay, so the next thing we're going to do once we determine the flow rates is estimate the energy loss due to pipe friction through each pipe, and then determine what is the pressure at each junction. Okay, so does everybody have these flow rates calculated? Is there any like step that I need to demonstrate again before we move on to calculating the head losses? Okay, so over here, let's put in a new column that says pipe H sub F. And we're going to calculate the head loss through the pipe in terms of meters. Does it already say that in your template or no? No? Okay. So add that. Because now that we know the flow rates, we're going to determine how much energy is lost as the water goes through each pipe. And remember that when we've calculated R values, which we have, H sub F is RQ squared. Okay, so here I just want to calculate the head loss through pipe AB. So it is equal to, here's my R, 10.3, times Q times Q squared. All right, so that tells me that there's 3.49 meters of head loss through that pipe, depending on its length, friction, diameter, and the flow rate that's going through there. So I've used the Darcy-Weisbach equation to estimate the head loss due to pipe friction, and I can drag this down and find the head loss through each of the pipes. And we should just double check, by the way, these common pipes to see if the head loss estimate's the same. So from the perspective of loop 1, it says that pipe CE lost 1.71 meters of head. Same thing here. From the perspective of loop 2, it comes up with the same estimate. So that's good. If they didn't match, that would mean that there's some issue. So EF has the same amount of energy loss through the pipe. So this is how much loss there is through each pipe. And what we're going to do now, I've drawn the final flow rates and flow directions into this sketch. Because now I'm going to estimate how much pressure there is at each junction by just looking at the starting pressure that we know at junction A and then subtracting pressure in the direction of flow and adding pressure when you're going against the flow. So for instance, at junction A, we know that the pressure is given as 600 kPa. And so how much head is that? Well, if we were given the elevation at each junction, then the head would need to reflect that. And we could account for the velocity head component of the energy, but let's neglect that because we've seen before how velocity head is generally a pretty small amount of the energy is tied up in velocity head. So let's cancel this out, and since we weren't given any elevations, it's told us in the problem statement that this is on flat terrain, so all of the elevations are the same. So Z sub D is 0. So the head is just the pressure divided by gamma. So how much energy is there at A? It is this pressure, 600 kPa, divided by the unit weight of water, which is 9.81 kilonewtons per cubic meter. So divided by 9.81. So there's 61.16 meters of head at A. Okay, now look at junction B. There should be less head at B than there was at A because the water is flowing from A to B. It wouldn't flow from A to B if B had more energy. It has to have less energy at B. That's what's driving the water through the pipe. So then the head at B is the head at A minus the losses through AB. And up here we calculated that the losses are 3.49 meters. So there's 57.67 meters of head at junction B. And what is the pressure of that? Well, pressure is the head times the unit weight. So the pressure at B is this head multiplied by 9.81 kilonewtons per cubic meter. So there's 566 kPa at junction B. All right. Now junction C. It's going to be however much head there was at B plus the losses through pipe BC, because we're going against the flow direction. So we're adding the head loss. And this is the same kind of stuff that you were thinking about in the homework assignment you submitted today. You know, that when you're going with the direction of flow, the pressure is decreasing. If you're going against the pressure, against the direction of flow, then the pressure has to be increasing. So the head at C is equal to however much head there was at B plus the losses through BC. There was such a low flow rate through that pipe, 0.019. We're going to find a pretty minimal change in head between the two. See how it was 57.672 versus 57.673? Not much head change. And the pressure is about the same as well. If I showed more decimals, I could probably visualize that difference in pressure. Okay, now what about junction D? So at junction D, there's as much pressure, as much head as there was at C, plus the losses through CD. So let me find pipe CD. Here's the losses. So I've got the head. I can calculate the pressure by dragging the formula down. All right. Continuing on, E. How do I determine how much head there is at E? Well, I'll start with junction C. So it is however much head there was at C minus the losses through CE. So I'll just subtract this 1.71 meters of head and then calculate the pressure at the junction. Lastly, F. I've got a couple of options to estimate the pressure at F. I could either say it's the head at A minus the losses through pipe AF, or I could say it's the head at E plus the losses through EF. I'll get the same answer either way. So let me just say it is junction A head minus the losses through AF. So that gives me the head at F, and then I can calculate the pressure at F by dividing the head by gamma. So now I've got the head at every junction and the pressure at every junction. And if we were in a design scenario here and we had criteria from our client, for example, that we could allow the pressures to go as low as 400, what that would enable us to do, if we were allowed to bring the pressures even lower than this, is maybe we'd play around with getting smaller diameter pipes and seeing if, you know, for example, if we reduced the pipe of EF, because that's pretty big, 700 millimeters, does it really need to be 700 millimeters? So what we would do in a design scenario is we would change one of the pipes. Up here at the very beginning, we would change the diameter, which would give us a different area. That's going to influence the F value, the R value. Everything would change from changing that diameter. And what we would find out is how did the pressure at that junction change when we changed one of the diameters. And that's the optimization process that you'll go through for the project this semester. But you're not going to be doing it with the spreadsheet. You're going to be doing it with WaterGems, which is some industry standard design software that's used all across the country. And it's easier to set up than a spreadsheet. So you'll love WaterGems by the end of the semester for sure. And I hope you'll appreciate the time that it saves you, because without WaterGems, you'd be setting up page after page of calculations like this. And you know, even this is an improvement over doing those calculations by hand. So that is the conclusion of this example. Does anybody have any questions before we move on from it? Anything I need to show again, or anything that wasn't clear? All right. Well, we've only got 2 minutes left. With that time, I wanted to give you a couple more Hazen-Williams problems, because you are very likely to see Hazen-Williams problems on the FE exam, and I want you to be prepared. All right, so let's look at the solution of these two together. Probably there wouldn't be enough time if I paused and had you go through the calculations on your own. So this first one, water flows through a horizontal ductile iron pipe, where on the basis of it being ductile iron, we know the resistance factor C. It has a diameter of 250 millimeters. The pressure is measured 75 meters apart, and the pressure measurements are 700 kPa and 685 kPa. What is the flow rate? So what I intend for this problem, if you look at the handout I've given you, is I want you to step through and recognize that, let's see, where do I have this? Additional, well, we'll go straight to this. Okay, the diameter in terms of meters is 0.25. Then from that we get the cross-sectional area, 0.04909 meters squared. And the change in pressure, 15 kPa, is the same thing as 15,000 newtons per meter squared. So you won't always have it laid out for you in a linear way like this on a problem, but when you're thinking about a pressure change, what you need to be, and you're going to be substituting it into this version of the Hazen-Williams equation where you've got S sub F. So S sub F is going to utilize the pressure change. And the way that it uses the pressure change is that H sub F, the energy loss due to pipe friction, is the change in pressure divided by gamma. Now that's only because this is a horizontal pipe. If the pipe wasn't horizontal, then there's more to it than that. You'd have to put in the full version of the energy equation to know how much of the pressure change was because of elevation change, and then how much of the pressure change is because of energy loss due to pipe friction. But here, if the pipe is horizontal, what that means is that any pressure change you see is because of pipe friction. If the pipe is not horizontal, then the pressure change is coming from two different things. It's coming from friction losses and elevation change. So this is a simplified problem because the pipe is horizontal. Since it's horizontal, delta Z is 0, and so we can just say that H sub F is delta P divided by gamma. So gamma here, if it says it's water, is 9810. So 15,000 divided by 9810 gives us 1.52 meters of head loss. Now, slope of the energy grade line, S sub F, is the head loss due to pipe friction divided by the pipe length. So now, if we know the slope of the energy grade line, that is where we're at the point that we could substitute it into here. So into the Hazen-Williams equation, S sub F, the slope of the energy grade line, we got, basically it's derived from the pressure change. Hydraulic radius, remember, for a circular pipe that's flowing full, hydraulic radius is the diameter divided by 4. So here I've got the coefficient 0.0. 140 is the flow rate. The diameter divided by 4 is the hydraulic radius. Here's the slope of the energy grade line. And I'm not sure why I put 0.0849, because the factor is 0.849, right? Who knows what I was thinking. The velocity should be 0.253 meters per second, and then to get the flow rate, we'll just multiply that by the cross-sectional area that we calculated before. So kind of like the heavy lifting on this problem, it's mostly just plugging into the formula, but the heavy lifting here is just analyzing it, knowing if it's a horizontal pipe, then that means the pressure change defines the head loss due to pipe friction, and the head loss due to pipe friction defines the slope of the energy grade line. So that was the first practice question I wanted to go through with you. The other one is a little bit unfamiliar because this is working in the traditional units. So pounds, inches, and so on. So this pipe is inclined. It is not horizontal. It's flowing through a cast iron pipe where we know the C value is 140, so that's not quite as smooth as the previous pipe we were dealing with. Diameter of 4 inches, and the velocity is given. So this time we're trying to find out what's the pressure downstream. When we know the upstream pressure, we know the flow rate. So we're using this formula to calculate how much head loss is there due to pipe friction. Okay, so the steps for this one is let's find out what is the energy loss due to pipe friction given the length of the pipe, its diameter, the velocity that's specified, and so on. So we're losing 39.82 feet of head. And then if we rearrange the energy equation, what we're trying to solve for is the downstream pressure, so P2. So here's the full version of the energy equation. And the velocity at 1 and the velocity at 2 are equal because the pipe diameter is the same. So V1 equals V2. And the only thing that we don't know is the pressure downstream, P2. So you can see all of the different components of it here. I switched the pressure upstream into pounds per square foot because it was given in terms of 72.5 pounds per square inch. So we have to multiply by 144 because there's 12 inches by 12 inches in a square foot. So I got 10,440 pounds per square foot. Then there's the elevation change that affects the pressure, the head loss, and so on. Multiply all of that by the unit weight of water in these traditional pounds per cubic foot units. So what you should get in terms of PSI downstream is 62.9 pounds per square inch. So I regret that we had to rush through that. Just to recap the announcements though, I'd recommend that you go ahead and do the Hardy Cross problem while it's fresh in your mind from the homework. And I'll see you on Monday because we don't have class on Friday. Have a good one.